Welcome to the class on IR spectroscopy. In this class, we will see some spectra and how to analyze uh, compounds based on IR spectra. Yeah, please go through this text. IR spectroscopy is also an absorption spectroscopy like UV visible spectroscopy. Generally, when a radiation of 8 to 40 kilojoules per mole is passed on to a material, it absorbs light. When it absorbs light, of course, it excites from the ground state to the excited state. So which transitions, when molecule absorbs energy, there will exist some transitions from ground state to excited state. Then which transitions are possible? Only those transitions which match with the natural vibrational frequencies of the molecule are absorbed. Now, among these transitions which absorb IR radiation, all these, whether these transitions are IR active? No, only those bonds that have a dipole moment that changes as a function of time absorbs the IR radiation. That means if the molecule possesses dipole moment initially, it is an IR active molecule. Alternatively, if the molecule is symmetrical, uh, that means its dipole moment is zero. But during the vibrations, if its dipole moment changes, then also it is IR active. So the basic selection rule for a molecule to be IR active is it should have a permanent dipole moment, or it should have some dipole moment during the vibrations. Only those bonds which possesses some dipole moment during the vibrations, they are only IR active. Thus, IR activity depends on the type of bonds and the structure of the molecules. Okay, so the structure will also, based on the structure also, whether the molecule is IR active or inactive, we can predict it. For example, diatomic molecules like hydrogen, chlorine, nitrogen, oxygen, they are IR inactive because they have only one bond whose dipole moment is zero. So they don't have IR activity, so that they don't exhibit IR spectrum. Similarly, this type of symmetrical molecules, they don't exhibit IR spectrum for C double bond C or C triple bond C. I am talking about double bond, okay? Because these are symmetric bonds, these don't exhibit IR spectrum. That means when you take the IR spectrum of these molecules, the C double bond C stretching frequency or C triple bond C stretching frequency, we may not observe these two things. Then IR spectroscopy gives the information about the types of bonds present in the molecule, thereby the functional groups present in the molecule. So as I said earlier, we can only predict the type of bonds present in the molecule, or from the type of bonds we can predict the functional group present in the molecule. But complete structural predictions is not possible purely based on IR spectroscopy. So that is why generally IR is not the sole spectroscopic technique used to identify organic compounds. Most of the time UV and IR, they are used to support proton NMR and carbon 13 NMR. Okay, these are not independent identification characterization techniques. Okay, right. So as I said, only those bonds which absorbs IR radiation, which changes the dipole moment, they are only IR active. So among the bonds which can absorb, which can change their dipole moment, there are two basic types of vibrations. One is stretching vibration, another one is bending vibration. A stretching vibration may lead to dipole moment change, or bending vibration may also lead to dipole moment change. Among the stretching vibrations, we have two different stretching vibrations. One is symmetrical stretching, where, for example, in this molecule, the two bonding electrons, they are pulled away from the carbon, so it is a symmetrical. So whether you are applying the force in the same direction, then it is called a stretching, symmetrical stretching. For example, if we pull these bonding electrons towards the carbon, both the electrons towards the carbon, then also it is a symmetric stretching. Then if you apply pressure one side towards the carbon, one and the other bond away from the carbon, it is called asymmetric stretching. So symmetric stretching and asymmetric stretching both will appear in the IR spectra, both will give their characteristic absorption frequencies. Generally we say for CH2 we do have two absorption spectra absorption bands below 3000. So these two are this is because of symmetric and asymmetric stretchings. Then again, in the bending vibrations, we have two different bending vibrations. One is in plane bending vibrations, another one is out of plane bending vibrations. Again, in plane bending vibration is classified into two types. When we apply the force in single direction, for example, when we are pulling these two hydrogens towards the up, then it is called rocking. Okay, when we are doing it towards the same side, then it is called rocking. Similarly, if we bend these two bonds in opposite directions, that means this bond is uh, bending downwards and this bond is bending upwards. So when we try to bend these bonds in opposite directions in the plane, then it is called scissoring. So when we bend the bonds in the plane in the same direction, it is called rocking. When we bend the bonds in the plane in opposite directions, then it is called scissoring. Similarly, out of plane bending vibrations, we have two categories. One is wagging, uh, uh, as you know, wagon wheel for railways. It pulls the two bonds in the same direction out of the plane. Okay, here these two hydrogens are pulled in the same direction out of the plane. So it is called wagging. Then when we pull these two bonds, one in opposite directions, that means this hydrogen is pulled towards left, this hydrogen is pulled towards right out of the plane, then it is called twisting. So bending, stretching vibrations, we have two different stretching vibrations, symmetrical and asymmetric. Bending vibrations also we have two types, in plane, out of plane. And in plane is categorized into rocking and scissoring. Out of plane is again categorized into twisting and wagging. Basically uh, these are called fundamental vibrations. uh, Whatever we have studied, stretching and bending vibrations, they are called fundamental vibrations. So whenever we observe some frequencies according to bending or stretching vibrations, we say these are fundamental vibrations. Of course, there are other vibrational bands like Fermi resonances, combination bands, overtones, then difference bands. Of course, we have studied them. Then uh, we also look at some more examples for symmetric and asymmetric stretching vibrations. This we have studied. Methyl group, we have symmetric stretching, asymmetric stretching is also possible. Anhydride, as I said, anhydride will exhibit two bonds, 1810 and 1780s, similar to that. Yeah. Why? Because it is having two stretching vibrations. One is symmetrical stretching, another one is asymmetric stretching. Similarly, amine, for example, nitrogen bearing two hydrogens. We have discussed two signals with same intensities. Yes, for amines, we do observe two signals with same intensities. So they are basically because of stretching, symmetrical stretching and asymmetric stretching vibrations. Similarly, for nitro also we have discussed two n double bond O frequencies. To the that is because of symmetrical stretching and asymmetrical stretching. Now, what is the importance of IR? Of course, IR can be used to predict only the functional groups, but how extent we can utilize this? Yes, sometimes, IR can explicitly differentiate different compounds. For example, I have given some compounds with similar molecular formula. See, for example, we have given cyclobutanol, 2-butanone, vinyl ethyl ether, then this allyl alcohol, then aldehyde. At the same time, I have given these IR spectrum. IR spectra for all these compounds. Then how do we match them? How do we match them? It's a simple thing, For example, first take these two, ketone and aldehyde. Ketone and aldehyde, they will have characteristic C double bond or stretching frequency, very strong absorption around 1700. We cannot miss them, right? Right. So first two belongs to ketones, right? So sorry, first two belongs to aldehyde and ketone. Of course, aldehyde will be having a higher frequency compared to ketones. So among these two, you just look at which one is aldehyde, which one is ketone. So that means the molecule which gives you high frequency, that is aldehyde, the molecule which gives you low frequency, that is ketone. I think in this case it is aldehyde, it is ketone. You just need to look at the exact frequency values. Right. Now we will try to differentiate the other three compounds: cyclobutanol, 2-methyl, 1-propene, 1-ol, vinyl ethyl ether. Among these three, two are alcohols. As we know, alcohols can exhibit a strong band around 3200 to 2000 3400. Yeah, we can clearly see these two belongs to alcohols, right? So they are giving hydrogen bonded. These look like a broad in the sense they are hydrogen bonded, right? So this doesn't have that. That means it is for vinyl ethyl ether. So in by looking at each and every functional group, their characteristic vibrations, we can clearly identify which molecule it is. For example, this vinyl ethyl ether, it is having a double bond. So that means it's a CH vibrations will be more than 3000, right? So 3000 will be somewhere here. That means these are more than 3000. Sorry, this is 3000. So less than 3, these are aliphatic CH vibrations. This sharp band is alkene CH vibration. So that means we have both the aliphatic and unsaturation. Now, if you want to differentiate these two alcohols, yeah, one alcohol is cyclobutanol, another one is having a double bond. So using that information, we can differentiate these two. That means this compound possesses sp2 hybrid is carbon hydrogen bond more than 3000 centimeter inverse. Yes, in this case, you see this is aliphatic hydrogens. These are aromatic. Please mute yourself. All of you, please mute yourself. Right. So when we look at these two, yes, we can clearly say this is aliphatic CH, this is unsaturated CH. We have an additional band here. But here, you see, we don't have that, right? So we do have only aliphatic CH, at the same time a broad hydrogen bonded alcohol band. We don't have that uh, hydrogens on double bond, right? So this in this fashion, we can easily differentiate. We can easily differentiate different compounds using their IR spectra. But as I said earlier, it is not possible to completely identify the structure. So if you are given molecular formula, or if you are given molecular structures, and if you are given spectra and asked to identify them, yeah, it is possible. But without any of these data, with simple spectra, we cannot completely identify the molecule. Okay, right. Yeah, to identify the aldehydes and ketones, we have one more additional CH stretching and symmetrical stretching and asymmetric stretching vibrations for this, right? So which will give you a doublet around 2850 and 2950, right? So aldehyde possesses aldehyde CH bond vibrations. It gives a doublet. Look at this doublet. So this is the doublet for aldehyde proton, aldehyde CH bond vibration. Whereas in the ketone case, we don't have that doublet, right? And another important point, aldehyde will have higher frequency compared to ketone. So when we look at the frequencies clearly, we can identify that this is ketone, this is aldehyde. Okay. Now, when we will have a brief look at the intensities of different vibrations, I'll just discuss one or two bands. You know, we have studied about the characteristics C double bond or stretching frequencies, C double bond C stretching frequencies. You know, C double bond or stretching frequencies are very, very strong. At the same time, C double bond C stretching frequencies are very weak or medium. Okay, so sometimes it is possible to overlap C double bond O and C double bond C because of the presence of many C double bond C, or because the C double bond O sometimes may not be sharp, sometimes it may be broad. So in that case, it may overlap with the C double bond C, right? So in order to differentiate these two, yeah, C double bond O will give a very strong peak. At the same time, C double bond C will give weak to medium sized peak. At the same time, alcohol will give you a strong peak. Similarly, amine, of course, it is having two hydrogens, so it is showing doublet. But if it is having single hydrogen, then it gives a sharp peak, or if it possesses hydrogen bonding, it gives a broad peak like alcohol. So in order to differentiate between alcohol and amine peaks, yeah, amine peak will be a little lower in intensity compared to alcohol peak. So that is also possible. At the same time, CH stretching vibrations. CH stretching vibrations are also medium to weak to medium. So we cannot miss CH stretching vibrations also. So in IR spectrum, some bonds are strong, exhibits strong intensities. Some bonds exhibit weak intensities. Yeah, when we were given an IR spectrum, then we can identify functional group. Now, in order to identify the functional group, how we should approach the spectrum? You weren't given any molecular formula or compounds. Okay, you were just given the spectra and you were asked to identify the functional group present in the molecule. Then how do we approach the spectra? You know, in the first instance, we must go for C double bond because it gives a very strong peak at around 1700, right? From 1800 to 1650, it gives a strong peak. We cannot miss that peak. So when you get the IR spectra, first go for, if you don't know the molecular formula, if you don't know the structure, just go for C double bond. If you have that C double bond peak, then immediately go for carboxylic acids. If it is a carboxylic acid, it will give a very, very broad peak, right? From 3400 to 2400 centimeters. A very broad peak. This type of peak will not be observed for any other functional group. So if you have a carbonyl, and then if you have a very broad peak from 3400 to 2400, then we are damn sure that it is a carboxylic acid. If you doesn't have this broad peak, then go for NH peaks. If you have NH peak, if there is one hydrogen or nitrogen, it will give a sharp peak, or a if it has two hydrogens or nitrogen, it will give a doublet at around 3400 centimeters. If it is not a carboxylic acid, just look for amide. Okay, whether it is showing any NH bond vibrations or not. If it is giving peaks around 3400, a very small, broad in nature, very sharp peaks, yes, it is an amide. If it doesn't have any NH, then go for esters. How do we predict esters? We can predict the esters by looking at the CO stretching frequencies from 1000 to 1300 centimeter inverse. If you have CO stretching frequencies from 1000 to 1300 centimeters, yes, it is an ester peak. Generally, we may not predict 1000 to 1300 centimeter inverse, so we may not properly identify esters. Just wait for some time. We will also look for other functional groups. Okay, generally esters will appear around 1740, right? Esters will appear around C double bond or stretching frequency will be 1740. If you have 1740 and peaks between 1300 to 1000, then you can say it is an ester. Now, how do we go for anhydrates? Anhydrates will give doublet at around 1800. right? Aldehyde also gives a peak at 1725, but it gives two characteristic CH vibrations at 2850, 2750. So if it is an aldehyde, then we also have these two doublets. If you have a doublet, then it is an aldehyde. If you doesn't have any of these peaks, then it is a ketone. Okay, ketone also gives a peak, C double bond peak at around 1720. Apart from C double bond stretching frequency, ketones doesn't have any other characteristics peaks, right? So yeah, we need to come in this order. So first look for C double bond O. If you have C double bond O, look for carboxylic acid. If it is not, look for amides. If it is not, look for esters. If it is not, look for aldehydes. If it is anhydride. If it is not, look for aldehyde. If it is not, then it is ketone. Now, if C double bond Y is absent, then we will go for alcohols, because alcohols OH peak will appear from 3400 to 3200 to 3600. If it is hydrogen bonded, it appears around 3400, right? So go for alcohols. Otherwise, we also have NH peak in the same range, right? Sometimes NH peak will be very sharp compared to alcohol peak, and sometimes you may also observe a doublet if you have two hydrogens on the nitrogen. So don't miss that doublet. Okay, if you have two hydrogens on the nitrogen, you will get a doublet, so you can't miss that. Then go for ethers doesn't have any characteristic peaks. Of course, we will get CO stretching frequencies is from 1000 to 1300, but they are not generally many stretching vibrations will be observed there. So we may not predict that clearly. So if it is not alcohol or amine, then go for ethers. And if still you don't find them, then go for C double bond C. Generally, C double bond C stretching frequencies appear from 1400 to 1650 centimeter inverse. But remember, these C double bond C stretching frequencies are a weak to medium range, weak to medium in intensity. So if we have many peaks from 1450 to 1600, it may be an aromatic system. How do we confirm that it is an aromatic? Aromatics are C double bond C, alkene CHs will generally give CH stretching vibrations more than 3000, right? Aromatic CH will be observed at 3100. Alkene CH will be observed around 3050. So in that way, we can go for either aromatic or aliphatic. Then also go for, if they are absent, then look for this special range where we can observe C triple bond N 2250, C triple bond C 2150. If you observe some peaks here, don't confuse whether it is C triple bond N or C triple bond C. If it is C triple bond C and if it is a terminal alkyne, then it also gives a CH around 3300, but it is a very sharp peak. Okay, this 3300 centimeter inverse is a very sharp absorption band. Then go for nitro compounds, then hydrocarbons also don't give any characteristic peaks. Now we will look at the IR spectra, some examples. Then how do we identify the different absorption bands? How do we attach them for different functional groups? Now we will look at alkanes, long chain alkanes. Look at this example. This is N-decane. It has only sp3 hybridized carbon. So it will have only sp3 CH stretching frequencies less than 3000. Okay. So yeah, this is 3000. All these are less than 3000 and they are very strong. At the same time, it will also have a long chain band around 700, a long chain band, and then CH3 and CH2 bending vibrations between 1300 to 1500. Okay, if it is a pure alkane, then we can identify them. Otherwise, if it is a if it possesses other functional groups, we cannot identify these bands. Okay, right. If it is in nuzole is a mineral oil. I did tell you that we can disperse our organic compound in nuzole and we can take the IR spectra. Yeah, when we take the IR spectra by dissolving our compound in nuzole, sometimes see these sp3ch aliphatic ch vibrations will be confused, then ch3ch2 bending vibrations, then long chain band vibrations, they all appear if the molecule is alkane. And if you want to try dissolving in nuzole and take the spectra, then it gives a complex structure, right? So you cannot identify the structure. So that is why generally we don't prefer nuzole. Yes, nuzole is also a long chain aliphatic compound which gives their characteristic peaks. This is for cyclohexane. We have only aliphatic CH stretching vibrations, then CH2 bending vibrations, no long chain band vibrations. When you want to look at the alkenes, yes, it gives is sp2ch vibration around 3050. Then it also gives OVP peaks from 650 to 1000. Then it gives a C double bond C peak from around 1600. We will look at some examples, right? See this example. Yes, we have sp2 hybridized carbon CH vibrations. They will appear more than 3000. They will appear more than 3000. So this is an example for that. It has a aliphatic CH, it has a unsaturated CH. So both are appearing here. At the same time, this is double bond OOP peaks, double bond OOP peaks, then C double bond C stretching frequency. Don't try to identify all the peaks. In IR spectra, we do get many peaks than what we are supposed to. So don't go for don't go for interpretation of all the bands, okay? We just need to pick the bands which will match with our compound. You just ignore additional bands. Okay, just ignore the additional bands. Similarly, for cyclohexene, yes, we have aliphatic CH vibrations, unsaturated CH vibrations, then CH2 bending vibrations. Here we also get additional peaks. This is C double bond C, cis alkene stretching vibration, and this is for cis alkene stretching OOP, cis double bond OOP, cis double bond stretching. Similarly, we also have this, in this case, it is a cis. So you have cis stretching, cis OOP. In the below spectrum, you see, it is a trans compound where we do have trans stretching, but it is very minimum. Sometimes we may not observe this intensity also. Okay. Similarly, we don't have trans OOP. Okay, so there is a trans OOP. The difference between cis OOP and trans OOP is that cis OOP will be observed around 700 centimeter inverse, whereas trans OOP will be observed around more than 900 centimeter inverse. So in this way, we can also differentiate both cis and trans compounds. When we look at the alkynes, yes, see alkynes, C triple bond C, we cannot miss this band because in this range from 2400 to 1800, we don't observe any other peak, right? So absolutely in all cases, it will be free. But if you have a C double bond, C triple bond C or C triple bond N, then you will get this, right? So if you have C triple bond C, yes, we do observe this 2150 centimeter inverse. Then for terminal alkynes, we have CH stretching vibrations, which appears around 3300 centimeter inverse. These are all aliphatic CH stretching vibrations, right? See, here it is an internal alkyne where we don't have this 3300 stretching vibration, right? At the same time, C triple bond C stretching vibration is also missed in this compound. Why? Why? Because it is a symmetrical alkyne, right? It is a symmetrical alkyne. As I said, in the case of symmetrical alkyne, we don't have this C triple bond C stretching vibration. Just look at these things. I have explained it in the last class itself. Okay. So yeah, you take the notes. Okay. Right.